This is the next video in this series of videos that describe how to compose the behavior of units. And in this video, we're going to be looking at communication device and message models. So I have the same scenario up that I was using in the previous video, and I've dropped that sensor model that I altered when I turned on terrain masking. So I'm going to I'm going to close a lot of these windows off now. So here's my unit, and up until this point, the blue shooter, we've got 8 models attached to this guy, 2 cognition models and a bunch of other models. And as you remember from the previous video, if it's been a while, I'll just show you this guy is all set up, and he assesses and takes a shot, and he kills the hostile target. So if you remember from the video on sensors and data processors and subsystems, I had a pretty lengthy description of what it meant to simulate perceived truth. And I talked about the fact that we believe the proper way to model perceived truth is to allow every participant in this scenario, in our case, every unit in this scenario, to have their own unique perception of their environment around them. And because that's the way it is in the real world. Every human has their own perception. We talked about the fact that perception is gathered by the local sensing capability of the unit, and that's the way it is in the real world. And it's also formed by information that we receive from other units. And in the real world, if it's 2 humans close to each other, they can talk with each other verbally. But other than that, some sort of a communication device is required in order to transfer information. Some simulations don't simulate communication explicitly. Others just had a flag to say, well, can these guys communicate or not? In Flames, you don't have to simulate communication either, but we recommend that you do. And just like all the other types of modeling that can take place in a simulation, we have very robust support for communication modeling. So the heart of that is a class of equipment model that we call a communication device. And so you can create subclasses of communication device to be able to build equipment models that transmit information between each other. And then we have another class of model. It's really not, we don't really call it a model, but it is another class. It's a message class. And the message class doesn't have any methods. It doesn't have any behavior associated with it. It's just a data structure, basically, that we inherit in order to be able to get a header on the subclass, on the subdata structure. And then you put whatever fields you want in the data structure. So it's basically just a data structure designed any way you want to with a Flames standard header on the front of it. So that's a message, and we have very well-defined processes for defining communication device models and for communication device models to send messages with actual content. It doesn't do any good to set a bit and say we can communicate. It doesn't do much good. What you really need to do is make sure that your communication devices are sending actual content, and that the cognition model that receives the content is using just that content to form its perception. So in Flames, we send messages with real content. In this particular set of models, the tutorial models, we have just a couple of very simple messages, as is true for all the models in tutorial. We keep it very simple so you can learn about Flames instead of learning about the details of how to model specific types of systems. We have a very, very simple comm device. And even if the comm device is simple, it's still important to model the process of storing data in a message, transmitting the message to another unit, and then let the receiving unit pull that data back out. Even if the comm devices that send that data are pretty simple, still it's a very, very important part of the formation of perception, is actually taking data from one unit, transmitting it, and delivering it to another unit. Of course, in a more realistic scenario, modeling communication is real important. You might lose a communication node, and when you do, all of a sudden, all of that information is just gone. You just don't get it. If you model communication explicitly, you don't have to do statistical degradation of performance just whether or not COM is there. You can actually really take out a COM node, and then the data that would be going over that communication path is not there. And then the units on the other side, on the receiving side, don't have that information available to them, and performance and effectiveness degrade very naturally in a much more realistic way, because it really is based on which particular data is being lost. So again, we have a very simple communication device model and just a couple of messages, and we have some cognition models that are using those models. And so it turns out that and we're already using one of them, but we're going to enhance this scenario just a little bit, just to show you how communication device modeling works and how messages work. So we've come up with a very simple example. We're going to take this particular unit right here, this blue shooter. We're going to go to his commands, and we're going to turn off his ability to choose his own targets. We're just going to not do assess. So if I don't do assess, and I run this scenario, even though that sensor model is gathering up track data, because the human is not looking at targets, he's never going to shoot. So I take that step. Now I'm going to add another blue unit to this scenario. And I'm going to make it a copy of my blue shooter to start with, and then I'm going to make some changes to its composition. So I have this thing called a blue commander, and I'm put it in edit mode, and I'm going to move this commander over here a little bit. And so he's just over here. And right now has the exact same composition. But what I'm going to do for this commander is I'm going to take some things off. I'm going to let him still have a sensor, but he's not going to be somebody who shoots. So he's not going to have a munition or a weapon system. And I'm not going to use the same cognition model. I'm going to let him use a different cognition model that we have written called the blue commander, or the commander cognition model. So I hit accept, and let's see what's the problem here. Oh, yeah, it knows that it needs a communication device, of course. So I'm not going to change this, and I'm going to employ a communication device. So employ COM device, and I've got one class of COM device and one meta object based on that class. I just call it blue radio, and I hit accept, and so now it's happy. So now you can look over here. He's got a COM device. He's got the same sensor and data processor. He's got a platform. And his cognition models now are the driver and the commander. So he doesn't have a shooter. He's got a commander type cognition model. So let's go take a look at this communication device. Very, very simple. It is infinite capacity. It doesn't degrade the communication at all. The only thing that we have to have in order to be able to allow two communication devices to talk to each other is they have to have the same channel. So if I want to set up a network of guys talking to each other, like the red guys, I could put them on channel 2, and then their messages would all only go among themselves. And then, but if I have two devices that both have channel 1, then those guys are going to be able to talk. So I put that on my commander, and I'm also going to put it on my shooter. So I'm going to go to his composition. And I'm just going to go to my commander, and I'm going to triple click on that guy and do a copy. And then I'm going to go to my shooter, and I'm going to add a COM device right here. And it doesn't, the order in which devices are added here doesn't really matter in general. You can put them in any order. It does matter about the initiate statements, though. If you're going to have an initiate statement, You need to make sure that or in other words, have a command. You need to make sure that the cognition model that defines that command has already been employed. So that's really the only restriction on the order in which statements are above here and in the order that you compose things. So I've got a shooter that has a comm device on it. It's a clone of the same meta object. So I know that the networks are set the same, or the channels are set the same. So, oops, that's the radar. So I'll go to that comm device. Let's just check. So the channel, not the network, the channel. So he's got a comm device and he's got a comm device, and they're set to the same channel. So any messages that he sends are going to be received, and similarly, any messages the shooter sends are going to be received by the commander. The only other thing I need to do is tell the commander that that the shooter is the subordinate. So the commander will know that when it sees targets, he should command the subordinate to shoot. So I do that at the shooter level, the way I've written these models. So above or after the locating route doesn't really matter. I'm going to add a command here that says assign commander. It's a command that I haven't used before. And it needs the name of a commander, so I can double click here and I can go click on this guy. So I have now specified that this blue commander is my commander. And I'll tell you what happens when I assign a commander, and this is a command that I can see this here. I'm going to go add this again. This is a command that is defined by the shooter cognition model. So when I tell the shooter that you have a commander, that shooter will say, okay, that must mean that I'm not supposed to make my own engagement decisions. So even if I had put the assess command in there, I think it would ignore it. It would say, well, you gave me a commander, so I'm not going to do my own assessment. In the startup command for this particular cognition model, he actually sends information to the commander that registers this subordinate with this commander. So the commander knows that he has a subordinate that he can command to make engagements. So that all happens internally behind the scenes. It's done automatically. In order to see that, I'm going to go over here to my blue commander, and I am going to, I already have it. Yeah, since I made a copy, they're both logging output. So I'm going to see the cognition model that are processing for the commander, and I'm going to see the cognitions that are processing for the shooter. Now for the commander, since he's going to make the shots, I am going to tell him to do the assessment. So there's also an assess that's defined by this commander cognition model. So he's the one that's going to look for targets. And I'll do an accept. So I think now I have everything all set up. Let's first just play it and see if anybody shoots. Sure enough, the shot gets taken and the target gets destroyed. So let's go take a look at our execution output now and see what happened. So you can see now there's a lot more stuff happening here. So the commander initiates assess, and then we see the move the waypoint commands. We see the startup happening for the shooter. And this is the place where the shooter is communicating with the commander to tell him he's a subordinate. And it actually prints out this little message right here. So this message is coming from within the startup command, within this method, FEX shooter startup. And I'm printing out a message that says, I'm registering myself with the blue commander. When that startup occurred, a commander had been assigned. Sure enough, right there. So he does that. So the way he does that is this unit initiates a command internally for another unit. So that's a legitimate thing to do. You can normally, when you initiate commands internally within a process model or a cognition model, you're initiating commands for yourself. You make a decision, you decide you're going to do something else. So then you make a decision in there, you decide you're going to do something else. So all kinds of things are taking place internally. But it is possible for a cognition model attached to one unit to initiate a command for another unit. Now, you can do that anytime you want to, but We recommend that you do that very, very carefully, because what you're doing is you're saying that you're allowing two units to communicate with each other without using a communication device and a specific message, which really can't happen in the real world. We can't directly transfer information from the mind of one unit to the mind of another unit. And that's what was happening when we initiated command directly for another unit. The times that we would do that is when we believe that this information would be known somehow in the real world sort of automatically. So when this guy gets his mission and he gets out in the field, he's going to be told, this is your commander, and the commander is going to be told, these are your subordinates, and the network engineers are going to set up the radios, and they're going to make everything all work. And all that stuff is all going to be done somehow in the real world, and we don't really need to explicitly model the process that's doing that. It's not important for us to model it. If it is important for us to model it, then we would need to put in communication devices and do all that stuff. If it's not important for the scenario that we care about, we can just initiate commands directly, which is what we're doing here. So he initiates a command for the commander. So you can see here, now the blue commander has this command called register subordinate. And we pass into that command the ID of the unit that is going to be a subordinate. So within that method, a little message is being logged that says, hey, I'm the commander and I am registering this guy named Blue Shooter as my subordinate. So those messages in there give us feedback to let us know what's really happening. So later on then, in this scenario, the assess executes for the commander, and he sees a target, and in this case, the target is within 1,000 meters. So why does it say 1,000 meters? So we go to the commander, and he has an assess, and it's because the assess has an input value called search range. So remember, for the shooter, when he was trying to figure out the range within which to look for targets, he went to the munition that was attached to him and looked at the max range of the munition. Well, this commander doesn't have any munitions attached to it. So it's kind of a simplistic thing. We just said, well, we'll just put a range on this commander, and we will say that any target outside that range, we just won't consider it to be a target. Again, we're doing this not because it's realistic. We're doing this just to illustrate different ways that you can do things in Flames. And you can look at the source code for this model to see how this works. So that's what we decided, because the commander may not be co-located with the subordinate. So we just said, look, we're just going to put a range on it. We could set that range to be 5 kilometers, what we know to be the range of the munition. So, but we just set it to 10 in this case. So that's why it said it was looking for targets within 10,000 meters, 10 kilometers. So sure enough, it found a target named Red Truck, and it assigns it for engagement, and it has its own internal method called assign target. And normally when a commander is doing that, we have this separate step to assign a target because we can't engage it ourselves. So this kind of takes the place of engage. In a more realistic cognition model, there might be a place where we're prioritizing the targets, and then we have another place where we're selecting which guy's going to shoot in case we have multiple subordinates. We pick the one that's available and the one that's closest. Then it can get a lot more complicated. In the starter models, it is a lot more complicated. There's a lot more sophistication that goes on in selecting a target and passing it off to a subordinate. But this is a very simple model. We simply just send a message. And so, sure enough, we have this logging. It also turns on logging for communication device models. So what happens inside this assigned target is he creates a message, and then he gives that message to his communication device model and says, I want this message to be transmitted. So the communication device model itself, this communication device called Blue Radio, transmits a message called an engage message. So you can't see that here. That's all down inside. You have to go look at the documentation of the source code to see what the content of that message is. An end user doesn't need to see those details. But he internally prints a message out of that comm device model that says, I'm transmitting this message to a target for a red truck. So all that is happening there. Now, on the shooter side, we have logging turned on for the communication device model. Remember, this log output turns it on for cognition and comm devices. And we see that he receives the message. So then we see there that he processes the message. So the communication device receives the message, and the message is passed to a method of the cognition model. So now this is FEX shooter, process engage message. So the comm device gets it, passes it to the cognition model. The cognition model looks at it, and he prints a message that says, I've just been commanded to engage the red truck. So he then engages. So this engage is the same engage that he would have initiated if he was doing his own assessment. So he initiates engage, and then that's what launches the missile. And he sends a message back. Well, these messages are actually coming from the track data processor. So he's actually sending track messages out. So we see that happening, and the blue shooter is sending these track messages out. So the commander, he's receiving the track message, so that's fine. So we see it's all going through here. And then let's see, those are all track messages. So here's engage, and here's where the missile gets launched. So we initiate the gauge, and then the engage actually executes at some time later, signifying the amount of time it would take to actually go find the right button and push it after getting that message. We transmit a, let's see here, let me read this. So we got more track messages going back and forth between guys. They both have sensors. They're both sending messages back and forth to each other. And then, so that's all just track stuff, track. And eventually the missile detonates, and we get an evaluate damage command initiated. By the way, that command is initiated internally within Flames. Commands like startup and evaluate damage. There's about 8 or 9 different commands that Flames initiates for units automatically when certain important scenario events take place. And so that's just built into the framework. And one of these is evaluate damage. So whenever a munition that a unit launches engages and detonates, it impacts the target, and that munition tries to damage a unit, evaluate damage automatically occurs. Now, you got to be careful about that. In the real world, you have to know, would I have line of sight to that target? Would I be able to tell with this pair of binoculars or something like that whether I was able to damage, whether I know if that target was actually destroyed? Again, that's all the perception thing. You may have to have a sensor that's you make sure the track is gone. So if it's a radar and an airplane's out there, you might not say it's destroyed until the track disappears because you can't see the airplane. So you got to be careful about that, and you got to make sure that you're modeling this part of the formation of perception realistically as well. In this particular case, we're cheating. We're assuming that we have line of sight, or that there's somebody on a hill that saw it for us. So we know the truth about whether or not we engage the target. So here's where we're evaluate damage is executing, and we say, yep, we know it got destroyed. So then the blue shooter transmits a message to his commander, and it's another engagement message. In this case, it's we set different information in there to tell the commander that the engagement is complete and that we actually destroyed the target. So our commander doesn't know whether or not the target gets destroyed until we tell him. So we send that message. The commander gets the message. It processes the message. And then we have a message in there that says processing engagement complete for the truck. And then we go out and look for more targets. So we initiate assess again. And so this particular commander is designed to only command engagement for one subordinate on one target at a time. So while all this stuff is happening, assess is not being initiated. But as soon as we get the message back from our subordinate that says, hey, I'm done with the engagement, the commander goes back out and starts looking for other targets. So what I've talked about here a lot is not just communication device models. I've talked about a simplistic flow of information, of a workflow, if you will, about how commanders engage subordinates, subordinates take the shots, subordinates communicate back to their commanders. I talked about a simplistic way of doing that, but it's all based on communication device models. The way that the commander and the subordinate talk to each other is through communication device models. So this is an opportunity for us to teach how communication device models are used in Flame scenarios. And again, you've got the source code to the messages, the comm device models, the cognition models that are sending and receiving all these messages. And so you have a way of looking at how this is actually done in the code. So again, communication device models are very important. I'll make a mention of one of the ways that we use this there's a lot of Flame simulations that are used for training of live systems, live command and control systems. There are some people that work on interfaces. There's like CISO standards for how simulations should communicate with command and control systems. In Turnion's opinion, those standards should never be defined. Real world command and control systems already have ways that they talk to other systems in the real world. And it's hard enough to define those interfaces, those standards, but they already exist. When we bring simulations into the mix, we want to do a live constructive exercise. We don't define it. We shouldn't, in Turnion's opinion, define additional standards for how do simulations talk to communication device or to command and control systems. No, you don't do that. You require the constructive simulation to talk to the live systems using the way that those live systems talk to other live systems in the real world. That's the interface. The interface is already defined. It's very robust. It works in the real world. You make your constructive simulations use that exact same interface. You don't do anything else. So in Flames, that's one of the reasons why we model communications so explicitly. And if we're working with a realistic simulation, a realistic scenario with realistic models, we are modeling with communication devices the actual flow of real military messages all amongst all the units with content that is representative of real military messages. Now, internally, the format of those messages are just C++ data structures. We don't pack all the bits up and use the right message protocols internally. But in terms of content and the way those messages are sent and who they're sent to and when they're sent, we modeled that all explicitly. So we've got Link 16 messages flowing all around inside our system to all the right players at all the right times, and we're modeling comms explicitly. Because we're doing that to communicate with a real world communication C4I system, we just take the messages that are already flowing inside the system and we pull them out, we reformat them into real tactical, real TattleJ format, and then we send them to the communication device using the hardware that the communication device actually uses. So the JREAP-C standard, for example, is Link 16 over internet, and a lot of modern command and control devices use JREAP-C. They have tactical internet connections. So we tap into that same tactical internet with we build a custom plugin for Flames that communicates over the tactical internet, and we translate that message into real TattleJ format, and we send it over the tactical internet to the C4I system using its real communication systems. And there's other systems. Sometimes it could be a serial port, it could be ADSI, it could be a radio emulator, whatever it might be. We send over real content, and the command and control system doesn't know the difference. doesn't know, unless we have a bit set in the message, that this isn't coming from a real world system. You don't modify the C2 system at all. You just let it use its real tactical systems. And because Flames can very easily put plugins for custom interfaces, we can talk to anything. We have one of our command and control systems. There's a real world sensor, a radar, a phased array radar. It has in the real world, it has a fiber optic cable from the radar down to the command and control system. And it has a very specific message protocol that it uses to send raw detection data to the command and control system. We implement that radar inside of Flames. We send the exact message protocol straight into that same port on the communication system, on the C4I system. And so that C4I system, C2 system, thinks it's talking to a real phased array radar. And we do that all the time. And there's never reason to do it any different. You allow simulations to talk to real world systems. If the real world systems already have an established mechanism for communicating with the outside world, you use that mechanism and you make the constructive simulation adapt to that mechanism. So you throw away all your C2 interface standards. Those are not necessary. Well, I'll get off my soapbox, but that's one of the reasons why modeling communication is so important, and one of the ways that we leverage that in building C4I trainers. We build the trainer for the U.S. Air Force Air Operations Center. That is a Flames-based simulation. So every air operations center in the world has an embedded training system, and we communicate with that all those AOC systems using the actual interfaces of those AOC systems. We build the trainer for the NATO Combined Air Operations Center, NATO CAOX. We build it for that. We build the trainer for the Marine Corps Common Aviation Command and Control System. All those systems talk to those live command and control systems, all those simulations, using real military interfaces. So communication is a big deal. It's really not that hard, but it makes the difference in the utility of the simulation in many cases. So thank you for listening to me pontificate. I hope I didn't cause you to cancel this video earlier. Thank you for listening, and thank you for using Flames.